Orbitrap Mass Analyzer. Dr. Michaela Sigilova. Bremen, Germany. Orbitrap Analyzer, an electrostatic trap. Ions trapped in an electrostatic field. Central electrode kept on high voltage. Outer electrode is split and able to pick up an image current induced by ion packets moving inside the trap. Z. Phi. R. Then ions move along a strange spiral which has three components. Rotational movement with frequency of rotation. Radial movement with this frequency. Axial oscillations along the central electrode. Only one of them is completely independent on energy and position of ions, that is the axial frequency. Therefore, only this frequency could be used for mass analysis. This is where ideal Kingdon trap becomes a mass analyzer, the Orbitrap. A. Makarov, Anal. Kim 2000, 1156-1162. 2. Ion injection and formation of ion rings. An ion packet of a selected MC enters the field. Increasing voltage squeezes ions. Voltage stabilizes and ion trajectories are also stabilized. Angular spreading forms a rotating ring. R, Phi, R, Z. Detection of ions. Ion packets enter the analyzer slightly off axis. The field inside the trap affects an oscillation of the ion packets/rings. The moving ion rings induce an image current on outer electrodes. The frequency of harmonic oscillations is proportional to ions mz. Fourier transform. Mathematical operation transforms frequency signal into a time domain spectrum. Orbitrap is a Fourier transform-based mass analyzer. Baron Joseph Fourier. Sigilova et al. Mol. Cellular Proteomics 2011, 10, M111.00094331. From an analyzer to a mass spectrometer. Plus. Detection of ions fragmentation. Ultra-high resolution. Accurate mass. Orbitrap Analyzer, the heart of a mass spectrometer. Q-Exactive Orbitrap Elite. 1.5x. The Orbitrap Elite is now the first instrument that uses the new high-field Orbitrap Analyzer. The high-field Orbitrap is actually smaller in size compared to the standard Orbitrap. The outer electrode diameter shrank by a factor of 1.5, whereas the diameter of the central electrode only shrank by a factor of 1.2, making the central electrode relatively thicker. This arrangement creates a higher field, making the ions going forth and back at an almost 2 times higher frequency, resulting in an almost 2 times higher resolution. And, because the little hole where the ions enter the Orbitrap also shrank, an additional lens was implemented to focus the ions more effectively into the Orbitrap, resulting in a higher ion transmission. 1.2x. Standard Orbitrap. High-field Orbitrap, resolution, key performance characteristics. Q-Exactive Orbitrap Elite. Res setting. MC400. HZ. 12.500. 12. 25.000. 7. 50.000. 3. 100.000. 1.5. Res setting. MC400. HZ. 15,000. 7.7. 30,000. 6.9. 60,000. 4.0. 120,000. 2.3. 240,000. 1.2. 480,000. Developer's Kit. Resolution. Why is it important? Enables accurate mass. Increases confidence of identification. Improves quantitative accuracy. Gives access to qualitatively different information. Figure shows the detection of 2 species with a mass difference as small as 0.015 omu at different resolution settings on the Q-Exactive instrument. The 2 species are not resolved at 35,000 FWHM, which results in a mass shift and an inaccurate detection and quantitation for both species. The two species are separated to 50% valley at 70,000 resolution, and baseline separated at 140,000 resolution. Therefore, higher resolution, in this case 140,000 FWHM, allowed for more reliable identification and accurate quantitation. At such high resolution, more than 200 species can be separated in a unit mass window. This translates into resolving, in theory, greater than 100,000 species in the mass range of 300-1000 AMU at any one point in time. This greatly reduces background interference and enables confident identification and quantitation of the target peptides in the presence of very complex backgrounds. More on the topic, in Cortez Francisco et al., Accurate Mass Measurements and Ultra-High Resolution, Evaluation of Different Mass Spectrometers for Daily Routine Analysis of Small Molecules in Negative Electrospray Ionization Mode. Anal. Bionl.chem. 2011, 400. 3595 to 3606. Mass accuracy, what for? N equals 14.0031. O equals 15.9949. S equals 31.9721. C equals 12.0000. Mass measured. Tolerance, Ta. Suggestions. Calc mass. 32.0 +/0.2 O2 Kio N2H4 S 31.9898 32.0261 32.0374 31.9721 32.02 +/0.02 32.0257 +/0.002. But here is the interesting thing, only the mass of 12C is a nice round number, 12. All other elements are either a tiny bit larger, H, N, or a tiny bit smaller, O, S. They show a so-called mass defect. If we can measure with enough accuracy, then this mass defect can effectively exclude some of the compound suggestions. In ideal case, just a single elemental composition, a particular combination of selected elements considered within certain limits, will remain. Mass accuracy is thus a powerful filter. A large number of elemental compositions, peptide candidates, can be excluded just by applying a simple filter, maximum allowed mass deviation. Accurate mass is a powerful filter. HR/AM analysis, identification. Increases confidence in identification. M plus H plus 381.07828. Mass accuracy. Number of hits. 200 parts per million. 265. 100 parts per million. 133. 30 parts per million. 39. 10 parts per million. 14. 5 parts per million. 5. 3 parts per million. 4. 340. 350. 360. 370. 380. 390. 400. 410. MC. 10. 20. 30. 40. 50. 60. 70. 80. 90. 100. 110. 120. 130. 140. Relative abundance. 381.07828. Compounds containing no. HR/AM analysis, quantitation. Improves quantitative accuracy by effectively removing background. Selectivity is built into the high-resolution analysis. MC 496.3398. +/2.5 parts per million. MC 518.3241. GP-CHO, 18-30:0. High resolution ensuring selectivity in phospholipid analysis. Extracted ion chromatograms for MC 496.3398 and MC 518.3241. The top two traces are shown for 2.5 parts per million windows, and bottom traces for 7.5 parts per million. Only using the 2.5 parts per million windows, top two traces, the extracted ion chromatogram for MC 518.3241 is specific for GP-CHO, 18-30:0. Increasing the uncertainty allowance yielded the incorporation of other masses. After increasing the ppm window to values greater than 2.5 parts per million, it was no longer possible to distinguish two important N+22 species, generated by either sodiation or the addition of two carbons and a further unsaturation site. Data courtesy of Gary Waffenden, Thermo Fisher Scientific. MC 496.3398. +/7.5 parts per million. GP-CHO, 18-30:0. GP-CHO, 16:00:0 plus Na. MC 518.3241. Coleman et al., Rapid Commune. Mass Spectrum. 2009, 23, 1411-1418. Mass accuracy across the elution profile. 21 scans per elution peak. External calibration. RD. 1.72 to 1.96. 1.75. 1.80. 1.85. 1.90. 1.95. Time, min. 10. 20. 30. 40. 50. 60. 70. 80. 90. 100. Relative abundance. 477.23016. HR/AM, another dimension in your data. Reveals fine isotopic structures. Separation of isobaric species in standard LC-MS/MS analysis. The 34S isotope containing peak is clearly resolved from the 13C2 isotope. Michalski et al., MCP 2012, 11.310.1074/MCP.0111.013698-1. Intact protein analysis. Complete charge state envelope with Humira. Major glycosylation forms or baseline separated. Relative intensity reproducibility within a few %. 5 micrograms of MAB were desalted and diluted from a ProSwift RP10R. Monolithic column using a 15 minutes gradient and analyzed using ESIMS on the Q exactive. The was MAB eluted over 1 minute as shown in A. The average spectrum over the elution time shows a nicely distributed complete charge envelope of the MAB. B. A zoom-in view of each charge state reveals 5 major glycosylation forms that are baseline separated. C. How Z. A complete workflow solution for intact monoclonal antibody characterization using a new high-performance benchtop quadruple Orbitrap LC-MS/MS thermo application node 2012. Intact protein analysis. Mass measurement accuracy. Average error for 34 measurements 6.9 parts per million. Standard deviation 6.4 parts per million. Mass deviations from expected target masses. For the 5 most abundant glycoforms, the average ppm error for all 34 measurements was 6.9 parts per million with a standard deviation of 6.4 parts per million. This indicates that the Q exactive is a very powerful platform for confirmation of protein primary structure. Confirmation of protein primary structure. How Z. A complete workflow solution for intact monoclonal antibody characterization using a new high-performance benchtop quadruple Orbitrap LC-MS/MIS thermo applicator Node 2012. Sequence confirmation of MAB. ETD fragmentation of an intactic Humira. Resolution settings 240,000 for fragment detection. Increased sequence coverage. Localization of modifications, dimidation. Not identified, possibly an internal fragment ion. Even 240,000 might not be enough for resolving this complex MS/MS spectrum. SW needs to subtract intensities, the same way as extract is doing it. Spectrum is an average of 10 spectra, each with 10 microscans. 7.5 s for each the scan, add overhead/fill time. About 2 minutes averaging. Separated by HBLC, BioBasic-C4, 100 ul per minute, 10 centimeters, 1 millimeter ID. Load, 5 micrograms on column. Gradient, 20 to 80% B10 minimum 0.1% FA. Column overloaded, elution time about 5 minutes. Dissolve in water, 1 microgram/L, injected 5 ul. Marcus Kelman, Orbitrap Elite Data. Spatially resolved HDX. Structural dynamic studies by measuring backbone amide HDX. Problems. Back exchange under quench conditions. Gas phase hydrogen scrambling. Figure 1. Schematic drawing of the cooling device adapted to a chip-based nanoflow electrospray ionization, ESI, setup. A flow of nitrogen. Gas cooled to sub-zero temperature is generated by passing it through a coil of copper tubing immersed in dry ice. The inset shows how the cold gas flow is directed to the front of the pipe tip, containing the sample solution, that is in direct contact with the ESI chip. The labeled parts are A. Entrance cone of Orbitrap mass spectrometer, B. Holder for ESI chip, C. ESI chip, D. Holder for conductive pipe tip, E. Conductive pipe tip, F. Outlet tubing for cold nitrogen gas, G. Copper tubing, H. Dry ice, and I. Thermoinsulated box. Only the front end parts of the nanomate are shown. Figure 4. Dissecting the solution structural dynamics of the terminal. Half of ubiquitin. Deuterium levels of the C fragment ions of ubiquitin after native state D to H exchange for 60 minutes measured by electron transfer dissociation mass spectrometry, filled circles, and NMR, red line. Error bars represent average plus/minus SD for measurements made in triplicate. NMR deuterium levels were obtained from exchange rate constants determined by Johnson et al. Ref 39. The theoretical deuterium content in the case of 100% gas phase HD scrambling is indicated, dotted gray line. The inset displays the crystal structure of ubiquitin, PDB1UBQ, the turn between beta strands 1 and 2 and the loop between the central alpha helix alpha 1 and beta strand are highlighted in red. See text for further information. Regions of secondary structure of the N-terminal half are illustrated above the figure for reference. A nearly perfect correlation is observed between the deuterium content of the C-ion series and the graph showing the cumulative deuterium content obtained from known NMR exchange rate constants 39. Compare filled circles with red graph in figure 4. The cumulative deuterium graph exhibits a distinctive profile, where the horizontal region of the graph from C6 to C11 corresponds to a flexible region in ubiquitin that is devoid of deuterium, a turn between beta strands 1 and 2, whereas the neighboring protected regions, beta strands 1 and 2, retain deuterium and exhibit a nearly linear increase. Sub-zero temperature in the ion source. Not compatible with pepsin digestion. Perform top-down analysis in HRMS. No gas phase scrambling with ETD. D assigned to individual residues. HRETD- black circles, Inamair, red line. Oman et al., Anal. Chem. 2012, 84, 4467. HK97 bacteriophage capsomers 253 kDa. Analysis of protein complexes. Extending the mass range. Protein assemblies up to 1 million Da. Ig antibody 150 kDa. HK97 bacteriophage capsomers 253 kDa. Yeast proteasome 730 kDa. E. coli grow L 801 kDa, ligand binding stoichiometry. 2000, 4000, 6000, 8000, 10,000, 12,000, 14,000. MC. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Relative abundance. 11,122.79. R equals 2048. 10,821.94. R equals 2161. 11,279.60. R equals 2002. 11,441.23. R equals 1873. 10,537.11. R equals 2186. 11,607.90. R equals 1600. 11,780.59. R equals 1353. 8,521.29. R equals 1342. 10,266.99. R equals 2252. E. coli grow L. 801 kDa. Orbitrap mass spectrometry of native protein complexes up to 1 MDA. Rebecca Rose, Eugene Demick, Edward Denisov, Alexander Makarov, Albert J. R. Heck, ASMS 2012. Orbitrap Elite and the proteome. Heat map of peptides eluting over 3 minutes interval in a 40 th range. Parallelization of data acquisition, a survey scan of 240,000 resolution with 20 SID scans all within a 2.7 s cycle time. High resolution MS scan at 3 different transient lengths. Followed by 20 SID MS/MS scans in the linear ion trap. Note that cycle time is unaffected by the resolution of the full scan. Preview refers to the portion of the survey scan that is used to select precursor ions for fragmentation. B. LCMS heat map of peptides eluting over a 3-minute solution. Time interval in a 40 th range. More detail is visible in the ultra-high resolution setting, left panel, compared with the normal resolution setting. Right panel. 3 minutes. 40 th. 148,000 peptide clusters x 93,000 peptide clusters. Michalski et al., MCP 2012, 11.310.1074/MCP.0111.013698-1. Data-dependent acquisition, issues. Run-to-run reproducibility. Inability to effectively target peptides of interest. The DDA sampling strategy offers an elegant simplicity and has proven highly useful for discovery-driven proteomics. Of recent years, however, emphasis has shifted from identification to quantification, often with certain targets in mind. In this context, faults in the DDA approach have become increasingly evident. There are 2 primary limitations of the DDA approach. First, is poor run-to-run reproducibility, and, second, is the inability to effectively target peptides of interest. 8. Hundreds of peptides often co-elute so that low-level signals often are selected in one run and not the next, and selecting M/Z peaks to sequence by. Abundance certainly does not offer the opportunity to inform the system of pre-selected targets. Overlap between various combinations of duplicate analyses of yeast peptides. AD, Venn diagrams displaying the overlap of different trials of the same dissociation method, CAD and CAD, A, ETD and ETD, B, SID-X SID ETD X ETD. Swanee DL, McAllister GC, Kuhn JJ, Nature Methods 2008, 5, 959-964, Proteome Analysis in a Single LC/MS Run. Rapid and robust proteome analysis. 50 cm column length. 4 hours gradient. 35 UC, nano-UPLC. Near complete yeast proteome. More than 4,000 proteins/run, 1% FDR. Median sequence coverage 23%. Figure C. The median sequence coverage of individual runs after matching is around 17%. The median sequence coverage from the combined run for 4,206 proteins was 23.4% as shown. D. The conjoined circles represent the frequency of identification of proteins in the 6 runs. Proteins identified in all 6 runs are designated as core proteome in the innermost circle. Single runs of fast-prepared and digested lysettes. Proxen Easy Nano LC 1000 use of long columns with linear velocity of 250 nl per minute. In the temperature range of 35 UC. 50 cm column with 75 meters inner diameter, packed in-house with 1.8 meters C18 particles, Dr. Musch GmbH, Germany. To facilitate deep sampling of the proteome, we employed relatively long columns and small particle sizes, 50 cm, 1.8 meters. This was readily accommodated by the UPLC pump, which produced a stable flow of 250 nl per minute at 500 bar. Another advantage of the UPLC system is its ability to load sample at a higher flow rate and to equilibrate columns more quickly, leading to a shortening of overhead times. We found the combination of a 50 cm column in 4 hours gradients to be a good combination for standard use. Minimum undersampling. Nagraj et al. Systems-wide perturbation analysis with near complete coverage of the yeast proteome by single-shot UPLC runs on a benchtop Orbitrap. MCP 2011, M111.013722. Data-dependent decision tree. Decision tree-driven tandem mass spectrometry for shotgun proteomics. Now, let's have a look at the behavior of phosphopeptides at harsher collisional conditions, such as those experienced in a quadrupole or multipole, TOF, HCD on Orbitrap. The above examples are fragmentation by HCD, when the high-resolution tandem mass spectrum of the phosphopeptide was obtained in the Orbitrap analyzer of an LTQ Orbitrap Velos, Thermo Fisher Scientific. The presence of a complete series of fragments at the peptide bonds, each measured with mass deviations of a few parts per million, and the presence of fragments that include the phosphogroup, unambiguously identify the peptide sequence shown, as well as the phosphorylation site at SER225. N and B anions are fragments at the NTH peptide bonds that contain the amino terminal part of the peptide, whereas anions contain the carboxy terminal part. NL, normalized intensity level, counts per second. What you do not find in the spectrum is the pika of the dephosphorylated intact peptide, neutral loss peak, which was so prominent for ion trap-based spectra. The next slide shows another example confirming this behavior of PS/T peptides under HCD conditions. Swanee DL, McAllister GC, Kuhn JJ, Nature Methods 2008, 5, 959-964. Product-dependent trigger, HCD-PDETD. Zoochilic separation of a glycoprotein digest. Targeted analysis of in-link glycopeptides in complex mixtures that does not require prior knowledge of the glycan. structures or pre-enrichment of the glycopeptides. Despite the complexity of N-glycans, the core of the glycan remains constant, comprising 2 N-acetylglucosamine and 3 mannose units. Collision-induced dissociation, CID, mass spectrometry of glycopeptides, results in the formation of the N-acetylglucosamine, GLUCNAC, oxonium ion and A, mannose plus GLUCNAC, fragment, in addition to other fragments resulting from cleavage within the glycan. In ion trap SID, those ions are not detected due to the low MZ cutoff, however, they are detected following the beam type SID known as higher energy collision dissociation, HCD, on the Orbitrap mass spectrometer. The presence of these product ions following HCD can be used as triggers for subsequent electron transfer dissociation, ETD, mass spectrometry analysis of the precursor ion. The ETD mass spectrum provides peptide sequence information, which is unobtainable from HCD. Full FTMS scan, MZ 380-1600, and subsequent HCD-MS/MS scans of the 40 most abundant ions above an absolute signal intensity threshold of 500 counts. If peaks at MZ 204.09, hexNAC oxonium ions, or 366.14, hexNAC oxonium ions, plus minus M/Z 0.05, were within the top 20 most abundant peaks. A supplemental activation, SA, ETD-MS/MS scan of the precursor ion in the linear ion trap was triggered. Figure 1. Online acyclic liquid chromatography HCD product. Ion triggered ETD-MS/MS of least C digest of ribonuclease B. A. Survey scan mass spectrum recorded in the Orbitrap at retention time. RT 25.16 minutes, B, HCD-MS/MS spectrum of precursor ions with MZ 645.6194, C, supplemental activation ETD-MS/MS of precursor ions with MZ 645.62. Singh et al., higher energy collision dissociation, HCD. Product ion triggered electron transfer dissociation, ETD, mass spectrometry for the analysis of N-linked glycoproteins. JPR 2012, DOI, 10.1021/PR300257C, product dependent trigger, HCD-PDETD. HCD fragmentation spectrum of MZ 645.6194. Oxonium ions observed among top 20 peaks. Figure 1. Online acyclic liquid chromatography HCD product. Ion triggered ETD-MS/MS of least C digest of ribonuclease B. A. Survey scan mass spectrum recorded in the Orbitrap at retention time. RT 25.16 minutes, B, HCD-MS/MS spectrum of precursor ions with MZ 645.6194, C, supplemental activation ETD-MS/MS of precursor ions with MZ 645.62. Singh et al., JPR 2012, DOI, 10.1021/PR300257C, product dependent trigger, HCD-PDETD. ETD fragmentation triggered. Peptide sequence information. Glycosylation site localization. Figure 1. Online acyclic liquid chromatography HCD product. Ion triggered ETD-MS/MS of least C digest of ribonuclease B. A. Survey scan mass spectrum recorded in the Orbitrap at retention time. RT 25.16 minutes, B, HCD-MS/MS spectrum of precursor ions with MZ 645.6194, C, supplemental activation ETD-MS/MS of precursor Ions with MZ645.62. Singh et al., JPR 2012, DOI, 10.1021/PR300257C. The newest and data-dependent acquisition. Instant spectral assignment. Algorithm processes tandem mass spectra in real time. Takes 16 ms to execute. Enables autonomous, real-time decision-making by the MS system. Real-time prediction of peptide elution windows en masse. Significant improvement of quantitative precision and accuracy. Boosted rates of post-translational modification site localization. The DDA sampling strategy offers inelegant simplicity and has proven highly useful for discovery-driven proteomics. Of recent years, however, emphasis has shifted from identification to quantification, often with certain targets in mind. In this context, faults in the DDA approach have become increasingly evident. There are two primary limitations of the DDA approach. First, is poor run-to-run reproducibility, and, second, is the inability to effectively target peptides of interest. 8. Hundreds of peptides often coalesce so that low-level signals often are selected in one run and not the next, and selecting M/Z peaks to sequence by abundance certainly does not offer the opportunity to inform the system of pre-selected targets. Bailey et al., Instant Spectral Assignment for Advanced Decision Tree-Driven Mass Spectrometry. PNAS 109, 8411-8416, 2012. The newest and data-dependent acquisition. Post-translation modification site localization. Ambiguous position from HCD. Trigger DTD resolving the ambiguity. The DDA sampling strategy offers inelegant simplicity and has proven highly useful for discovery-driven proteomics. Of recent years, however, emphasis has shifted from identification to quantification, often with certain targets in mind. In this context, faults in the DDA approach have become increasingly evident. There are two primary limitations of the DDA approach. First, is poor run-to-run reproducibility, and, second, is the inability to effectively target peptides of interest. 8. Hundreds of peptides often coalesce so that low-level signals often are selected in one run and not the next, and selecting M/Z peaks to sequence by abundance certainly does not offer the opportunity to inform the system of pre-selected targets. Bailey et al., Instant Spectral Assignment for Advanced Decision Tree-Driven Mass Spectrometry. PNAS 109, 8411-8416, 2012.